This is part 3 of lecture 5.2, finite sets. In this video, we will obtain the cardinality of the power set of a finite set and state the pigeonhole principle and some of its consequences. At the end of this video, you are expected to be able to use these theorems to write short proofs of statements involving finite and infinite sets. Our first result is another counting formula that is a consequence of the principles of counting presented in the previous video. For any finite set A, the power set of A is finite with cardinality equal to 2 raised to the cardinality of A. Recall that the cardinality of a finite set is the number of elements in the set, and thus is equal to a non-negative integer n. Thus, to prove the result, we need to show that for any non-negative integer n and for any set A, the cardinality of A is equal to n. If the cardinality of A is equal to n, then the cardinality of the power set of A is 2 raised to n. We shall prove this by induction on n. For the basis step, assume that n is equal to 0. Let A be a finite set with cardinality 0. Then A is the empty set, so the power set of A consists only of the empty set. And thus the power set of A has cardinality 1, which is equal to 2 raised to 0, which is equal to 2 raised to n. So the result holds for n equals 0. This concludes the basis step. We now go to the inductive step. Let k be a non-negative integer and assume that the claim holds for n equals k. That is, assume that for any set B, if the cardinality of B is k, then the cardinality of the power set of B is 2 raised to k. We need to show that the claim holds for n equals k plus 1. That is, for any set A, if the cardinality of A is k plus 1, then the cardinality of the power set of A is 2 raised to k plus 1. Let A be a set with cardinality k plus 1. Choose an element small a of the set A and define the sets curly x and curly y as follows. Curly x is the set of all subsets x of A which do not contain the element small a. And curly y is the set of all subsets y of A which contain the element small a. It is left as an exercise to show that curly x union curly y is equal to the power set of A and that curly x and curly y are disjoint. Applying the first counting principle to the sets curly x and curly y, we conclude that the cardinality of the power set of A is equal to the cardinality of curly x plus the cardinality of curly y. It is left as another exercise to show that curly x is equal to the power set of A minus the singleton consisting of the element small a. By a previous result, the set A minus the singleton consisting of small a has cardinality equal to the cardinality of A minus 1, which is equal to k. So by the induction hypothesis applied to the set A minus the singleton with element small a, the power set of A minus the singleton with element small a has cardinality equal to 2 raised to k. Thus, the cardinality of curly x is equal to 2 raised to k. Define the map from curly x to curly y as follows. For any subset x in curly x, the image of x under the map F is the set x union the singleton with element small a. It is left as an exercise to show that F is a bijection from curly x to curly y. Then curly x is numerically equivalent to curly y, so that the cardinality of curly y is equal to the cardinality of curly x, which is equal to 2 raised to k. Therefore, the cardinality of the power set of A, which is equal to the cardinality of curly x plus the cardinality of curly y, is equal to 2 raised to k plus 2 raised to k. This is equal to 2 times 2 raised to k, which is equal to 2 raised to k plus 1. This concludes the inductive step. Therefore, by the principle of mathematical induction, for any finite set A, the power set of A has cardinality equal to 2 raised to the cardinality of A. We now state the pigeonhole principle. Let n and r be positive integers, and let f be a function from the set of integers from 1 to n to the set of integers from 1 to r. If n is greater than r, then the function f is not 1 to 1. That is, there must exist two different integers in the domain which have the same image. We will postpone the proof of the pigeonhole principle to the next video. Instead, we shall use the pigeonhole principle to give a proof of the following result. For any positive integer n, the set of integers from 1 to n is not numerically equivalent to any of its proper subsets. That is, for any positive integer n and for any proper subset S of the set of integers from 1 to n, S is not numerically equivalent to the set of integers from 1 to n. To prove this, let n be a positive integer and let S be a proper subset of the set of integers from 1 to n. We need to show that S is not numerically equivalent to the set of integers from 1 to n. Then, by the definition of numerical equivalence, there exists for a contradiction, assume that S is numerically equivalent to the set of integers from 1 to n. Then, by the definition of numerical equivalence, there exists a bijection f from the set of integers from 1 to n to the set S. Two things may happen. Namely, either the integer n is an element of S, or the integer n is not an element of S. We shall consider each of these cases separately. For case 1, suppose that n is not an element of S. Then S is a subset of the set of integers from 1 to n minus 1. Hence, the bijection f is a function from the set of integers from 1 to n to the set of integers from 1 to n minus 1. And this function is 1 to 1. But the number n minus 1 is less than n. So by the pigeonhole principle, there is no 1-to-1 function from the set of integers from 1 to n to the set of integers from 1 to n minus 1. Thus, we have a contradiction. Therefore, S is not numerically equivalent to the set of integers from 1 to n. For case 2, suppose that n is an element of S. Since S is a proper subset of the set of integers from 1 to n, there is an object X belonging to the set of integers from 1 to n minus the set S. That is, X is an integer from 1 to n which does not belong to the set S. Let T be the set S minus the singleton with element n union the singleton with element X. That is, T is obtained from the set S by removing the element n and replacing it with the element X. Then, by construction, the set T does not contain the number n, so T is a subset of the set of integers from 1 to n minus 1. By applying the first counting principle to the sets S minus the singleton with element n and the singleton with element X, the cardinality of T is equal to the cardinality of S minus the singleton with element n plus the cardinality of the singleton with element X. Since the number n is an element of S, the singleton with element n is a subset of the set S. Thus, by one of the corollaries to the pigeonhole principle, the cardinality of the set S minus the singleton with element n is equal to the cardinality of S minus the cardinality of the singleton with element n, which is equal to the cardinality of S minus 1. The singleton with element X has cardinality 1. Therefore, the cardinality of T is equal to the cardinality of S. Hence, by the definition of numerical equivalence, the set S is numerically equivalent to the set T. Since, as we assumed at the beginning of the proof, S is numerically equivalent to the set of integers from 1 to n, it follows that T is also numerically equivalent to the set of integers from 1 to n. But by case 1, T cannot be numerically equivalent to the set of integers from 1 to n, so we have a contradiction. Therefore, S is not numerically equivalent to the set of integers from 1 to n. This completes the proof. The next result is a generalization of the previous corollary. If S is finite, then S is not numerically equivalent to any of its proper subsets. To prove, assume that S is finite. Two things may happen. Either S is empty or S is non-empty. If S is empty, then S has no proper subset, so the result is vacuously true. Suppose that S is non-empty. Then S is numerically equivalent to the set of integers from 1 to n for some positive integer n. Hence, there exists a bijection f from S to the set of integers from 1 to n. Let T be a proper subset of S. We shall show that T is not numerically equivalent to S. For the sake of a contradiction, suppose that T is numerically equivalent to S. Then T is numerically equivalent to the set of integers from 1 to n. By an earlier exercise, the restriction of f to T is a bijection from T to its image f of T. So T is numerically equivalent to f of T. Thus f of T is numerically equivalent to the set of integers from 1 to n. Now, since T is a proper subset of S, there is an element small s in the set S minus T. Since f is 1 to 1, this implies that f of S is not in f of T. Thus, f of T is a proper subset of the set of integers from 1 to n, since f of S is an element of the set of integers from 1 to n minus f of T. Hence, by the previous corollary, f of T is not numerically equivalent to the set of integers from 1 to n, and we have a contradiction. It follows that T is not numerically equivalent to S. This completes the proof of the result. You have come to the end of part 3 of lecture 5.2. Before you proceed to part 4, you are strongly encouraged to answer the exercises given at the end of these slides. Thank you for your attention.